conditional statements and their converse. So what we're going to look at in this section is how to understand and interpret conditional statements. So to start with, we're just going to go through a few definitions of what you're going to come across in this section, and then we'll apply some of it. So conditional statement is an if-then statement. For example, if it is Monday, then it is a school day. So that's the key right here with an if-then, or with a conditional statement. It has to have that if-then within the statement. A hypothesis, then, is nothing new for you. You've done hypotheses all the way along in school. An assumption, for example, in the statement, if it is Monday, then it is a school day. The hypothesis in this is, it is Monday. So a hypothesis you can look at as an assumption, a hunch, or a guess. And we'll do a little bit more with those. I was going to give you some more examples, but we'll do that later. Conclusion. The result of a hypothesis, for example, in the statement, if it's Monday, then it's a school day, the conclusion is it's a school day. Counterexample, then, is an example that disproves a statement. For example, if it is Monday, then it is a school day, is disproved by the counterexample that there is no school on Thanksgiving Monday. Only one counterexample is needed to disprove a statement. So as soon as you use a counterexample, if you can find one counterexample, that disproves a statement. You don't need to find more than that. Okay, number 5 is a converse. A conditional statement in which the hypothesis and the conclusion are switched. For example, the converse of if it is Monday, then it is a school day is if it is a school day, then it is Monday. So you're just switching the if-then to a then-if kind of thing. Or what was on the if side now moves to the then side. So by conditional, then, is a conditional statement whose converse is also true. In logic notation, a biconditional statement is written as P if and only if Q. For example, the statement if a number is even, then it is divisible by 2 is true. The converse, if a number is divisible by 2, then it is even, is also true. The biconditional statement is a number is even if and only if it is divisible by 2. Okay, so biconditional has that if and only if. So A can happen if and only if B is happening. Communication note here for notation. P with this double arrow Q is notation for if P then Q. And it's red P implies Q. So P in the two-way arrow, Q, is notation for P if and only if Q. This means that both the conditional statement and its converse are true. So the first one is a conditional statement, P with the arrow 2. Arrow Q is a conditional, and one that has the arrow going in 2 directions, so that's where the biconditional comes in, means that if and only if. Okay. So it says James and Gregory James and Gregory like to play soccer. Sorry, there we go. James and Gregory like to play soccer regardless of the weather. Their coach made this conditional statement about today's practices. If it is raining outside, then we practice indoors. When will the coach's conditional statement be true, and when will it be false? So what we need to do is we need to verify the conditional statement. So it says verify when the coach's conditional statement is true. So the hypothesis is if it's raining outside. Okay, so that's the kind of guess or the assumption that they're making. So we assume that if it's raining outside, the conclusion is we practice indoors. Each of these statements is either true or false. So to verify this conditional statement, consider 4 cases. So the first case that we're going to consider is the hypothesis is true and the conclusion is true. So that means that it rains outside. And we practice inside. When the hypothesis and a conclusion are both true, and a conditional statement is true. Okay, so if both the hypothesis and the conclusion is true, then we have a true conditional statement. The hypothesis is false and the conclusion is false. So the hypothesis then was if it rains, so then for it to be false is it does not rain. And opposite of practicing indoors is we practice outside. So when the conclusion and the hypothesis are both false, a conditional statement is true. The hypothesis is false and the conclusion is true. So it does not rain. Does not rain, and where are we? And we practice inside. So when the hypothesis is false and the conclusion is true, a conditional statement is true. Case 4 says the hypothesis is true and the conclusion is false. So in that case, it would be it rains outside, and the conclusion to be false would be and we practice outside. So when the hypothesis is true and a conclusion is false, then the conditional statement is false. So this here is a counterexample. So if you remember by definition there, a counterexample is number 4, an example that disproves a statement. For example, if it is Monday, then it is a school day. It's disproved by the counterexample that there is no school on Thanksgiving. Only one counterexample needs to disprove a statement. So that shows that the conditional statement is false. Okay, so that's just basically using the definitions that were, some of the definitions on that first page. When you're looking at a conclusion, or when you're making a conclusion, sorry, not a conclusion, a conditional statement, and switching your hypothesis and conclusion. So doing the 4 possible examples that you can. So this says use a truth table to summarize the observation. Let P represent the hypothesis. It is raining outside. Let Q represent the conclusion. We practice indoors. So we had when our if statement was true and our our then statement, so this is the if and the then, was true. our conclusion was true. Our conditional statement was true. When they were both false, if our if was false and our then was false, our P, and remember that P arrow Q means P implies Q, was true. When we had a false hypothesis and a true conclusion, our conditional statement was true. So the P implies Q was true. And when we had a true hypothesis but a false conclusion, then we had a false statement. So these two here are kind of a special case, because you've got false statements being said in there, yet we're still getting a true result. So when the hypothesis is false, regardless of whether the conclusion is true or false, the conditional statement is true. So you can make an incorrect hypothesis, but your conclusion can still be true to make your, it could be true or false, and your conditional statement will still be true. So from the truth table, I can see that the only time a conditional statement will be false is when the hypothesis is true and the conclusion is false. So basically, when you say this is going to happen, and this, let's say A is supposed to, when A happens, B will happen, and A happens but B doesn't, then you have a false conclusion. Because that's like saying, if I get all my homework done, I'm going to get 100%. Well, you could get your homework done, but do it all wrong. Therefore, you have a false conditional statement. Okay, so let's take a look at another one. A person who cannot distinguish between certain colors is colorblind. So to write this as a conditional statement where if P then Q will happen means that for this one what you're saying is if a person cannot distinguish colors, cannot distinguish between certain colors, then that person is colorblind. Okay, so that is our conditional statement if, where we say if P happens, Q happens. So P implies Q. If a person cannot distinguish between certain colors, then the person is colorblind. Write the converse of your statement. So remember, the converse, what it does is the hypothesis and the conclusion are switched. So that would be if a person is colorblind, then that person cannot distinguish between certain colors. So it's saying, is your statement biconditional? Explain. So biconditional means it's a conditional statement whose converse is also true. So a biconditional statement is written as if P, or P happens if and only if Q happens. So a person is colorblind only if and only if that person cannot distinguish between colors. So the first one says, so explain. So first let's take a look. Is the first statement true or false? Well, it's true, because if you can't distinguish between colors, then you could be colorblind. So that is true. Is the converse true? If a person is colorblind, then that person cannot distinguish between colors. Well, by definition, that's what a colorblind person is. The statement can be written as, a person is colorblind if and only if that person cannot distinguish between certain colors. Okay, next example says, verifying a conditional statement. Reed stated the following by a conditional statement. A quadrilateral is a square if and only if all of the sides are equal. Is Reed's biconditional statement true? So what is the conditional statement then? The conditional statement would be if a quadrilateral is a square. So basically what you're doing for a conditional statement, you're taking that if and only if. I'm just going to write quad is a square, then all of its sides are equal. So the converse of that statement would be that this should have if. Sorry, if a quadrilateral is a square, then all of its sides are equal. So the converse then would be if all of the sides of a quadrilateral are equal, then it is a square. So remember, what you're doing is whatever is after the then, so all of this becomes our if statement. If all, whoops, I wrote that twice. If all the sides of a quadrilateral are equal, then it is a square. So we're taking that all of the sides, moving that to the if, and putting the then it is a square as the flip on there. So if a quadrilateral is a square, then all of its sides are equal. Is that true or false? Well, that's true. In order for it to be a square, the sides have to be equal. The converse of that, if the sides of a quadrilateral are equal, then it is a square. Is that true? This is false. And that's because you could have a rhombus. A rhombus is still a quadrilateral. It's just pushed over, basically, right? So that would be our counterexample to prove that. So a rhombus has 4 equal sides. And so that means it's a parallelogram. So it meets 2 of the criteria. It has 4 equal sides and it's a parallelogram, but it's not a square. So therefore, the converse statement. And remember, in the definitions it said that you only need to have one counterexample in order to disprove your statement. So what this means that then is since I was supposed to put converse and I was putting since the converse statement is false, the biconditional statement, so that if and only if statement is false. Okay? So in order for something to be biconditional, it has to be true for both the conditional statement and the converse. Okay, the last page here is just kind of a wrap-up and a summary. So your key ideas: a conditional statement consists of a hypothesis P and a conclusion Q. Different ways to write a conditional statement include the following: if P then Q, P implies Q, or P the arrow Q. To write the converse of a conditional statement, switch the hypothesis and the conclusion. So need to know, it says a conditional statement is either true or false. A truth table for a conditional statement can be set up as follows. Okay, so basically what it's showing you there is you can have true and false hypothesis. I lost my word there. You can have a true or false hypothesis and still end up with a true conditional statement. But if your conclusion is false and your hypothesis is true, then you have a false conditional statement. So it says here, a conditional statement is false only when the hypothesis is true and the conclusion is false. Otherwise, the conditional statement is true even if the hypothesis is false. So it says you can represent a conditional statement using a Venn diagram with the inner oval representing the hypothesis and the outer oval representing the conclusion. The statement P implies Q means that P is a subset of Q. Okay, so that's like saying dogs are animals, or if a dog has 4 legs, then it's a mammal. Would work in there because our if statement is if the dog, and a dog is a subset of a mammal. Only one counterexample is needed to show that a conditional statement is false. And if a conditional statement and its converse are both true, you can combine them to create a biconditional statement using the phrase if and only if. Okay, so that biconditional, you have to be able to prove both the statement and its converse in order for it to be a biconditional statement. So there's your questions, 203 to 206, 1 to 8, and question number 12.